Hello, welcome back everyone. In this video we are going to continue our exploration of the properties of propositional logic. In the last video I sort of walked you through the idea of the main operator, right? And the main operator is really the most important logical operator that translates the crucial connective in any complex statement. So by now you should have a kind of comfortability with the idea of translating ordinary sentences into propositional logic in terms that use variables to stand in for statements and logical operators to stand in for connectives, right? So the connectives are translated with the operators like tilde for negation, dot for conjunction, horseshoe for conditional, wedge for disjunction, and the triple bar for biconditional. So in this video, we're going to continue that pursuit and have a look at what is referred to as the truth functionality of propositions. In other words, propositional logic allows us to sort of play with our logical operators in a way that discovers the truth value, the possible truth value of statements such that we can come to some understanding of whether or not arguments are valid and what their truth value are. So, remember that the logical operators serve to bring together or connect up simple statements into complex or compound statements. Simple statements are connected to one another with connectives or logical operators to form those compound statements. And so in a way, the variables are sort of less important than the operators, and the operators themselves are going to be the things that sort of are the driver of the sentence, with that main operator being the most important for any compound statement that has more than one operator. So remember, if we have our full chart here of operators, we have sort of symbols used to translate parts of speech that mean connectives, right? So negation, or our tilde, translates terms like not. It's not the case that. Dot, or conjunction, translates and, also moreover and but. Disjunction, we use a wedge to translate or unless. Also, either or is a disjunction, right? The conditional is translated with our symbol horseshoe, which translates if then or only if, bringing together an antecedent and a consequent, right, as its parts. And a biconditional is essentially the conjunction of two conditionals, and we use the symbol for a triple bar to translate if and only if. The biconditional, the triple bar, is the rarest logical operator in this set, but they do still occur from time to time, so you have to know it. So if we go to our example, Hamlet is a tragedy and Dune is a fantasy. We use H as a variable to stand in for H as a tragedy, and we use D as a variable to stand in for Dune is a fantasy, and we bring together those two variables with nothing more elaborate than the symbol dot to symbolize the the connective and. So that is all we need to translate a sentence like this. So I don't know, sometimes this can be confusing for students because that English sentence has so many different associations and connotations sort of packed into it, and yet we're able to boil it all down just to three symbols, right? But that is really sort of what we're after in propositional logic, because we are interested in formal structure much more than in content and the rich sort of meaning thick layers of context and value that might go into that content. So you might reasonably criticize propositional logic for being a little simplistic with our language, but that simplicity allows us to explore some other formal properties that we wouldn't otherwise be able to investigate. All right, so to describe truth functionality, we have to just sort of begin with some brass tacks. And the idea of truth value refers to whether or not a given statement is true or false. Remember, we are working with a totally binary system in terms of truth value. So statements in propositional logic are either true or false, right? There's no kind of gray area or ambiguity or anything like that. So in addition to Simplifying the meaning of language into really sort of bare bone structures, propositional logic also reduces truth functions to a binary kind of on-off, black-white system. The truth function is when a truth value of a compound proposition is determined by the truth values of its components and by the logical operators. So in other words, the truth function of a compound proposition is going to be determined by the arrangement of logical operators in any given complex sentence. And we're going to have to unpack concretely a little bit how this works and how we can come to an understanding of what the truth value of any given statement is. So a statement variable, we're going to use just variables to stand in for simple statements without operators, P, Q, R, and S. Again, these are arbitrary, right? We're just kind of going sequentially here to stand in for simple statements that don't require an operator. And the statement form refers to a pattern of statement variables in logical operators, such as this arrangement, which reads, it is not the case that either P or Q. Remember from our discussion of the main operators, the main operator cannot be in parentheses, so negation, in this case, tilde, is the main operator of this compound statement. And tilde, or negation, really is a negation of this disjunction, which brings together P and Q under the aspect of either or disjunction, right? Okay, so let's have a look at what are called truth tables. Truth tables are arrangements of the possible truth value of any given operator within our set. They show every possible truth value for compound propositions. So these can be a little overwhelming at first in terms of the sheer quantity of possibilities that can be laid out before us. But when we get familiar with what the rules are for each operator, it'll prove to be a really neat and clean way of discovering the truth function of complex statements. So you will have to spend a little time with these tables to understand how each operator has its own truth function. So the truth functions provide definitions for all logical operators that we've been working with: negation, conjunction, conditional, and so on and so forth. And they have a real uniform pattern. In other words, they don't change across time or depending on their context. So once you know the truth value of every operator, you know it, and you can plug it in to any complex statement. So here's the truth value for negation. This is an example of a truth table. It tells us what the truth value of a certain statement form, not P, is, given the value of the component parts. So if we look on the left-hand side, we have our variable P, and under P we have every possible truth value for the simple expression P. P can either be true or false. So we begin with true, and then the other option is false. So there are only two possible values for a simple statement P, right? It's a binary system, can either be true or false. And then if we set aside P and negate P, we have to essentially invert the truth value of P, because the negation of P is simply saying it is not the case that P. So that tilde essentially is saying it is not the case that whatever our value is the case. So if we begin with a true P, the negation of P has to be false. And if we begin with a false P, the negation of P has to be true. So negation is a very simple truth function, really. It's just the opposite of whatever our initiating truth value is. So to put this into ordinary language, if we have a simple statement like this, Moorhead State is in Kentucky, and we abbreviate that with the variable P. I could have used M to stand in for Moorhead, but it doesn't matter. And I know that that statement is true. It has a truth value of T. Well, we know that the negation of P then has to be false, and the translation of not P becomes it's not the case that Morehead State is in Kentucky. Excuse me. So that value is the negation of t, which has to be f, which is false. So we can just use t and f to stand in moving forward for true and false as abbreviations, right? So this should be pretty straightforward. If we begin with a simple statement that is we know to be true, the value of it is given as true, we simply negate it. It has to have the opposite truth value, false. Okay? So with simple statements, negation is pretty straightforward. Whatever that truth value is, we flip it. It becomes its opposite. What about conjunction? Dot. With conjunction, we are bringing together two conjuncts, right? Two different variables. The truth table definition for conjunction shows that for any combination of truth values, P and Q, it will have the following truth values. So for P and Q, we have two variables, so we need twice as many rows on our truth table to account for all the possible combinations of true and false that could occur for two variables. So the way we arrange this is we first of all on our these are on the left called the reference columns. Over here, the first two rows are reference columns. They just lay out, apologize for my writing here, they just lay out every possible truth value that could occur for a combination of P and Q. So we split the values of P in half with two true and then two false. And then for Q, we just simply split in half that value where we alternate true, false, true, false. So this accounts for every possible combination of the truth values for two variables, P and Q. And then we bring them together in our truth table with the dot symbolizing the conjunction and. Okay, so how do we notate the truth function for dot? Essentially, this arrangement, T, F, 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 refers to the value of dot. The rule for conjunction is that a conjunction will be true only when each of the conjuncts on the reference table are true, right? So have a look at our reference table again. If we begin with the first row, we see that the first two values are true. P is true and Q is true. And so based on our rule, we know that the first row of dot is true because both of the conjuncts is true. If we move down to the second row, I see that P is true and Q is false. So one of the conjuncts is false, and with conjunction we know that you need two true conjuncts for dot to have a true value. So our second row has to be false. Likewise, if we move to the third row, I see that I have a false conjunct under P and a true conjunct under Q. So because we don't have two true conjuncts, I know once again that the third value for dot has to be false. And finally, for the fourth row, I have two false values, a false P and a false Q. So because we have no true conjuncts for the fourth row of dot, we know that dot is false. So dot is only going to be true on the first row, where we have two true conjuncts. So it is only true in one instance. So if I look at a sentence like this, today is Friday and it is raining, and I symbolize the first conjunct, today is Friday, with P, and I symbolize the second conjunct with Q, it is raining. I know that for and to be true, I need both P and Q to be true, because the and is sort of contingent of the truth value of both parts of that sentence. I can't have just Friday being true or raining being true. I need both of those component parts to be true for and to be true. So conjunction has a very, how do I put it, a very high ceiling, a very high threshold for the dot to be true, for it to have a true value. In most cases, it is much more frequent for it to be false because it requires two conjuncts possessing true values to be true. Okay, now let's look at the truth functions for disjunction. The truth table definition for disjunction shows that for any combination of truth values PQ, either P or Q will have the following values. So let's have a look. Once again, on the left, we have indicated our reference tables to set off P and Q. The arrangement for the reference tables over here on the left are exactly the same as they were for the dot, because we have the same number of variables. We have P and Q, two variables. So we're going to have two values of true and two of false, and then we kind of split that 2 in half to have alternating values under Q, true, false, true, false. And now have a look at the values for wedge. When we bring together P and Q under the disjunction wedge, you'll notice I have 3 true values in the first 3 rows and 1 false value. So what could our truth function rule be? Well, it seems to be that disjunctions are false when each of the disjunct is false. They are true in every other instance. So only on that final row do I have a false disjunction, right? I have 2 false rows for P and Q on the 4th row of the reference table, and so wedge is false in the 4th row. In every other instance, wedge turns out to be true. I can have 2 true disjuncts and have a true wedge. I can have a true P and a false Q and a true wedge. And I can have a false P and a true Q and a true wedge. So the either or statement is sufficiently flexible that wedge can be true even if one of the disjuncts is false. They just can't both be false. If they are both false, if both P and Q are false, then the disjunction as a whole is false. So if we look at this ordinary sentence, today is Friday, or it is raining, all I need is one variable in the disjunction to be true. Either P can be true or Q can be true for wedge as a whole to be true. However, if both variables, P is false and it is raining is false, then the or as a whole is false. So unlike conjunction, which requires 2 true conjuncts for dot to be true, wedge only requires 1 true disjunct for wedge to be true. So it's a much lower threshold needed to meet for wedge to be true. And that kind of makes intuitive sense. If I say either it is sunny out or it is raining out, well, only one part of that speech has to be true in order for the sentence as a whole to be true, right? We don't need both parts of the disjunct of the either or to be true for the sentence as a whole to be true. Now let's look at the conditional, right? Our horseshoe. The truth definition for the conditional shows that for any combination of truth values, PQ, if P then Q will have the following truth values. So notice, once again, our reference tables are exactly the same every single time for 2 variables, PQ. We have 2 rows of true, 2 rows of false. We then split it in half for Q to have alternating values, true, false, true, false. So I want you to get in the habit of writing this down and writing out the whole reference table and coming to an understanding that the truth tables are always taking this pattern. Then have a look at horseshoe when we bring together P, if P then Q, where P is the antecedent and Q is the consequent. I have 2 values, 3 rows that have a true value, the first, the third, and the fourth. But the second row is false. And you might ask yourself, why? Well, look over to the reference table. I see that P is true and Q is false. So in instances where I have a true antecedent and a false consequent, horseshoe as a whole is false. And that simply refers us back to our original definition of validity when it comes to deductive arguments. Remember that deductive arguments are valid when a definition follows with with necessity from true premises. So if we have a true premise and a false conclusion, we know the argument is invalid, right? So this is just kind of reiterating for us that original definition of validity. So if we have a look here at our definition, a conditional will only be false, only when the antecedent is true and the consequent is false. All right, so you need to have that form, a true antecedent and a false consequent for horseshoe, to have a false value. You can even have two false values, with P being false and Q being false, and the horseshoe as a whole is true. That is very counterintuitive for students at first, to have two false values and yet have the truth value of horseshoe be true. But that is actually the case. It is only not working when we have this violation of validity. You can have a false antecedent and a true consequent, and horseshoe is still true. Okay, so it has a different truth value than conditional, negation, and disjunction. So if we look at this sentence, if you drive west on I-64, then you will get to Lexington. If we parse this out into an antecedent P and a consequent Q, well, so long as you're driving west on I-64, so long as this antecedent is true and this consequent is true, then we know that the horseshoe, the main operator, is true as a whole. So this whole statement is valid. It has a true value. All right, so conditional will take a little time to get used to in terms of understanding that the only time that a conditional doesn't work is when you have a true antecedent and a false consequent. What about the biconditional, our triple bar? Again, we're not going to see this quite as often, but you still have to know it. The truth table definition for the biconditional shows that for any combination of truth values for PQ, P triple bar Q will have the following truth values. So have a look at our truth tables over here. Again, we have our reference tables set off to the left for PQ with identical values as the last times, 2 values for true, 2 for false under P, and then alternating true false for Q. And then we have P triple bar Q, so this is the biconditional, and it seems that we have 2 instances in row 1 and 4 where triple bar is true, and 2 instances, row 2 and 3, where triple bar is false. So what is our rule? Our rule for biconditional holds that a biconditional is true when both P and Q have the same values. So notice that lines 1 and lines 4 have the same values. In row 1, they're both true, so triple bar is true. And in row 4, they're both false. So even though they're both false, they are identical. So triple bar becomes true. They're only false when we have differential values, when we have values that are not identical. P is true, or Q is false. Therefore, triple bar has to be false. P is false, or Q is true. Triple bar has to be false. So P triple bar Q has the same truth value as the conjunction of 2 conditionals, both if P then Q and if Q then P. Remember, triple bar is simply the conjunction of 2 conditionals offset in parentheses. Again, we're not going to see biconditional nearly as regularly as negation or disjunction or disjunction, but you do have to account for this truth function rule. Okay, that is our full set of truth tables. Now let's do a little practice. If we have an example like this, if x is if x then y is true, then which of the following is correct? Whoops. Let me get out of the way here. A, x must be true. B, X must be false. C, X could be true or false. Again, if X is Y is true, which of the following is correct? A, X must be true. B, X must be false. Or C, X could be true or false. If you said C, you're correct, right? If we have a look over at our truth table, we know that for any two variables PQ, the only instance where horseshoe is false is where we have a true antecedent and a false consequent. And we're given an answer here, a truth value of true. So that means that it is possible for X, our antecedent, to be false or true, right? Those still yield true values for the function of horseshoe. So horseshoe is a little bit tricky to pin down, right? There are a lot of possible options for horseshoe in terms of its truth function. It's just important to really key in on the property of a true antecedent and a false consequent being the dead giveaway of a false conditional. Let's have another look. If both R and S is false, then which of the following is correct? So we're dealing with dot, we're dealing with conjunction. A, R is true. B, R is false. C, R could be true or false. Again, if both R and S is false, then which of the following is correct? A, R is true. B, R is false. C, R could be true or false. If you said C, you are right. Notice that with conjunction, the only instance where dot or conjunction is true is when we have two true conjuncts. So if we are using PQ to represent RS, right, we have two variables, and we have this laid out, we can see that we can generate a false dot, a false conjunction from a true P, which stands in for R, or a false P, which stands in for R, right? So conjunction is sufficiently elastic. It has that high of a threshold such that if we know that if we know that conjunction is false, one of those conjuncts could still be true, right? Or it could also be false. So C is the right answer here, right? It could fall into row 2, or it could fall into row 3, and it could also fall into row 4 for that matter. All right, so you can see how the truth tables might serve us well when we get to really complex statements and we're interested in the truth values of them, because we can start to key in on these little rules that apply to each one of the operators. Let's look at another example. If either R or S is false, then which of the following is correct? So we're dealing with disjunction for two variables, PQ, and we're using RS to stand in for them. A, R is true. B, R is false. C, R could be true or false. So either R or S is false, then which of the following is true? A, R is true. B, R is false. Or C, R could be true or false. If you said B, you are correct. There is only one option on our truth table that indicates a false option for wedge for either P or Q, and that's where we have both of our disjuncts PQ having false values, right? So R has to be false because it's the only option where our first variable P is belonging to a false disjunction, right? So disjunction is more elastic than conjunction in terms of which it only needs one true disjunct for the disjunction as a whole to be true. So if we're told it's false, well, then we know we need two false disjuncts, right? So both P and Q, or in this case, both R and S, have to be false. So B has to be the answer. Okay, that is enough for now. We are going to pursue this a little bit further in the next video and start to begin to use these truth tables for more complex statements. So I encourage you, before moving on, to really make sure you've at least written down the truth functions for each of the 5 operators at least a couple of times, so that you can begin to be comfortable with them, and you start to learn the rule for each one and begin to see how they're different from each other. Because as we get to more complex statements, it'll become a little bit challenging for you to have to constantly refer back to the rules. So it is good to be able to memorize them as we move forward. Okay, so have a look over these functions again, and we will continue this next time.